It's really a pleasure, to now come back as a presenter. So here, what I plan to do is this. This is something I will share with our community. Something I've been thinking in the past few years as a both researcher, instructor, and mentor. Because we know this um, you know but science and engineering are two complementary but also different related different field. In science, we focus on understanding, while engineering, they thing is focus on to get something done, right? Get things done, get something perform optimal. So science, right? We provide guidance, right? Understanding that's for engineering, and though sometimes we also borrow ideas for engineering, right? Like especially in biology research, we often found it's uh, very fruitful if we using take concepts from engineering to as a reverse engineering look at biological systems. But recently years, I found out, okay, they're because all those big data, aging, very exciting, right? And this time I feel, there we see there's a confrontation of culture because physics and not physics, science and engineering, we definitely have different emphasis. So this is start let me to think about it, how we teach our students and also how we present our work to the larger community. So specifically, the reason I found out is I found, something when we were trained, we really, something we value a lot in our field now somehow becomes less valued. And some thing we really often taught not to, but now become some trendy. So like here, I show one example, like, in physics, right? We really emphasize simplicity. So we want to, understand what's the nature, the core, the basic things, and try to neglect a lot of less important details. But now, there see a lot of emphasis you see on using some very sophisticated uh, math, computational algorithm. So this has become an emphasis, right? While simplicity become less emphasized. Also, we often say, okay, when we work on something, it's not just you try to crack the machine to get things, rather you think, right? Um, you often say you guess, right? First think, then do the integral. This is where Rudolf Peres to Hans Bethe, and also John Wheeler said, never ever calculate until you know the answer, right? So often we really guess the answer, then we formulate the problem. But now you see there are a lot of when we in our current teaching, we emphasize a lot to teach our students some of those specific technical details, algorithms. They have the impression that, this is more important. Once they have that, they just crank the machine. And nowadays, the AI tools really kind of reinforce those kind of impression. And also, my advisor, George Auster, often tell us that you want to find the tools for the job instead of holding a hammer, look for a nail. Well, nowadays you also see this publishers, funding agency, all this lot of emphasis of try to develop various tools, competition tools. So the selling point is they will develop the tools, then users, let's say biologists, they do not need to know the details. They just use the tools, get something. So I feel this is very different from what I was trained, many of us are trained. So I asked the question, okay, so in this big data age, how we should, what's a unique thing for us, right? As a physicist, and do we have any unique strengths, and how we should interact with larger community? So I thought, okay, I would like to use some, what I think about my experience in the old days, see which in my experience really all what talked here really guide my research, and I want to argue this is also important in nowadays. So what I would like to talk is this old work starting. I start my first paper probably 26 on this bacterial Flagellar motor. Then, back and forth, I have been working on this because collaborators holding back. Even recently, we have a paper just online. So I would like to use this example to see how those principles guide my research. And also, this topic actually I seldom talk about, although it's something I'm very interested, I'm very proud of. So the background is this, we all know this E. coli swim, and shown here from Howard Berg's website. We know Howard Berg is our real hero in our field. He opened the whole field about chemotaxis, bacterial motility. He pioneered work to show, for example, here, this chemotaxis, cell sensitive environment eventually there's a bacterial Flagellar motor. He showed this is a rotary motor. So before his work, people think nature has not invented wheel. He is the one who demonstrated this rotary motor. Then later, Paul Boyer rebutted the idea and proposed that F1 ATPase is a rotary motor. For a long time, Paul Boyer was, his idea was regarded as nonsense. But later, then John Walker solved the crystal structure. And Kinoshita really demonstrated single molecule technique, so that F1 ATP is a rotary motor. Then Paul Boyer and John Walker shared Nobel Prize. But actually, all this idea come from Howard. Howard also, but we also borrow idea from on his work on the FO, F1, F0 ATPase, right? So I have some work on all of the three rotary motors. Yeah, so I think, really, Howard's contribute a lot to the field. I personally really believe, we the committee really owed him, we owe our community a Nobel Prize on this. So let's talk about this bacterial Flagellar motor. It's a very complex machine with many protein come together form this structure. So it's so you see have the rotary part, rotor, then have this shaft, then go to the flagellum, and then you have this this is a stator. There are several stators. It's embedded in the membrane. So it's the outer membrane, this cytoplasm membrane. The stator actually is anchored to the peptide glycan. So this is the structure. Then here's a movie from Namba's lab. His lab was, invest a lot of money to make these beautiful movies to show how this Flagellar motor. You see, this is rotary, and then it can reverse. See, this is can reverse direction to drive. This is the flagellum to rotate. So you see this flagellum bundled together. They work as a propeller to propel the cell body to move. Okay. So Howard have done a serious work trying to characterize this motor. So what they did is, so this is really the early work. You can vote this earliest work on single molecule. You can see that. So what they did, this is a flagellum, right? So they can, for example, anchor the cell body to a surface. Then you can chop the flagellum, then attach a bead there. So you can monitor from microscope, look at the speed size, rotation speed. So this is a low Reynolds number, right? A low Reynolds number environment. So then you can, so usually, you have this torque balance, right? The motor torque will generate that go outside, and also there's some stochasticity drag, this drag, right? So given this balance. So what they did is found out this Flagellar motor is very powerful, can generate 2,000 to 4,000 piconewton nanometer, torque, and also can rotate very fast. Some, proton driven motors can go fast as 1,700 hertz. So it's very fast. Much faster than the mammalian machine, actually. So Howard did, did this. They can attach different size to bead. Therefore, if you're big size, you have bigger drag, right? So then you will have slower speed. So they can measure, by doing this, you can measure the motor torque, and versus the speed. So they can measure this called torque speed curve. They can also vary the proton motive force. So here is a proton motor, it's a proton driven. Actually, there's another other motors can also driven by bacteria, for example, can also driven by sodium ions, but similar. So they found this, see, those the speed remains almost like constant up to several hundred hertz. There's a knee region, and the knee region suddenly drops almost linear drop. So there are several things. One thing is why this is almost constant, and also in calculus about close to what you can get based on thermodynamics, because you have ion motive force, you calculate how much free energy you can get, and then you calculate what's the theoretical limit of the motor torque. You see this very close to that. If you vary the proton motive force, it drops, at this region, essentially proportional to the proton motive force linearly. So this is all these puzzles. And this is one, so because Howard thought, okay, in this, this is very important for us to understand how this motor works. And also their belief that, all this relation reflect how they interact, rotor, stator, all these components interact each other. So Howard and also several other labs, they build many models, try different interaction potentials, try to play with them, try to do schemes. But, this remained unexplained for a long time to get those features. So when I was a postdoc at time, I got interested in this problem. So George actually tried to convince me not to work on it because he told me so many people have tried the field. So he suspects there may be something missing, some experiment component missing, information missing. So but at that time I got really interested in, so I continued to work on it. And also at the time, there's a visiting student from Richard Berry's lab at Oxford, Fan Bai. So we team up to look at this. So we thought of this problem. Let's think about what's going on. Clearly, all this data suggests, as I mentioned, there's this region's thermodynamic control, right? It's because you got the thermodynamic limit. Clearly, all the kinetic doesn't really matter. Then here is the kinetic controlled region. Okay, and there are evidence to indicate that this thermodynamic controlled region. Besides, I just mentioned another set of experiment Howard did is they just changed the temperature. They changed the temperature. They measured torque speed curve. We see this. This plateau region almost unchanged, but then this region you see indeed have temperature dependence. The temperature will change some chemical transition rates using Arrhenius relational thing, right? Well, you may argue, of course, that free energy also have temperature dependence. But if you think about it, right? Free energy have this entropy. If you plug in the number, this is I did it for the E. coli. You plug in the number, you see that the entropy term, the contribution is minimal compared to this transmembrane potential. So that agrees, right? Explains why there's not much temperature dependence. There's another experiment they did is they examined the motor speed in H2O versus D2O. Okay, because it have an isotope effect. That's again, it's a proton, right? Proton jump. We expect some isotope effect on jumping rate. And they also found out, for the plateau region, there's not much dependence on the isotope effect. But in the knee region, there's strong dependence. So this also agree that this is a plateau region thermodynamic controlled, and in this region is kinetic controlled. So this is what the first round we can guess what's going on. So with this, let's give some thinking about. So this is a homework when I teach biophysics, I always assign this homework to the students. I made up this one. Mainly, I want to think about it, right? So, this is thermodynamic consideration, how you can get maximum work. Let's go back to our introductory thermodynamics. And what do we know it? Well, how you get maximum work from a process, let's say the constant temperature. What do you do? Let's think about this PVT system chamber, gas chamber. Well, we know from our second law of thermodynamics tell us what you need is, this process reversible, right? If this piston moves infinitesimally slow, then the gas expansion, we can get the free energy change. That can be mostly utilized for work, right? This is something we know from thermodynamics. And also we can get some intuitive understanding what's going on. See, clearly this shows in this system what I mean. When we have piston moves, you think about it, right? When you move, you generate some vacuum. Then those gas molecules, they need to relax. Relax, try to fill the gap to reach a new equilibrium. And essentially here we're talking about two time scales. One time scale is the piston movement. Another is the relaxation time of the gas. So when we talk about infinitesimal, we really mean, we need this two time scale, right? The piston moves much slower than the gas relaxation time. You can also think about this, right? We know if the piston moves very fast, then you have much less work. Infinite fast, essentially, you do not get work. And also it get some mechanistic, no, mechanics view of what's going on, right? What's work? Work is the force times the displacement caused by the force. So what's the force? Force is because the gas molecule bombards this piston, then that will have an impact on this the piston. So in order to do this, when you have a moving piston, you have some velocity along the direction. Then you see the molecule. Then along you see this this gas molecule. They have the component, right? The vertical component velocity. Then you see they to catch this piston. Then have collision. Clearly, you see if the gas the velocity component less than v, then those molecules won't be able to catch this piston contribute to work, right? When the piston moves infinite fast, then there no gas molecule can catch. That's why we got zero work, right? So the key thing here, you have two-time components. So let's see how about this Flagellar motor system. Can we identify the time scales? So what I asked students to do is let's do some back envelope calculation. One thing I told them is, okay, in the motor, there's some internal dynamics, the iron hopping on, off. That's about millisecond time scale. And let's think about the motor rotation. Well, if in a motor rotation, there are about two ions will move down each step. Each step is we have 26 units. So each ion hopping corresponding to 52 steps, one of 52 steps, right? So you can calculate that distance about rotation about 2 pi divided by 52. So if you plug in the number, you find out, it's about, say, the motor moving around 200 hertz or something. Then you see this rotation time scale still about 10 times faster than the internal dynamics. So we still have this time scale separation. So that one give you a hint how you can generate this, have this thermodynamic efficiency. Okay, so how you have this two time scales? It turns out, there's old work by Howard Berg, Steve Block. They really measure, and David Blair, they really measure the flagella. They found that the compliance is elasticity, especially that's come from the hook. Okay, so that's this in the hook allows existence two time scale in the system. Again, right? You see the one is internal dynamics, that's a chemical reaction. So time scale about 1/k. And also you have this because the hook, right? This elasticity. So you have drag. They will have this relaxation time, the spring, which is given by the drag, and this kappa, the spring constant. So the two time scales. Therefore, you see immediately see what's the requirements. Here I haven't talked about anything about the exact details, the interactions. What matters is the two time scales. If you have the two time scale separation, you got this region. And this region is where, when you change your bit size, eventually there's crossover. So that gives you this connected controlled region. So, and also in this thermodynamic control region, you got this, right? Because the thermodynamic controlled, you have the linear dependence on the proton motive force. So, okay, so this is a general consideration. Now let's see, think about it as an engineer, see how can we make a protein motor. So in order for protein motor work, what's the basic ingredient? The first thing you have a protein motor. As a machine, you have some mechanical motion. So how can mechanical motion? Here is illustrate a simple idea, right? Suppose you have two components. Then, let's say initially, let's say there's a charge. There's a charge here. There's a charge, but neutralized by movable ion. So neutralized. But then if the ion helps, now your interaction between these two components, you start have Coulomb attraction, then system try to relax to the local new energy minima, right? So the key point is there are chemical reaction that switch the system from one potential curve to another, then result in this mechanical motion, lead to a new, relax to a new energy minimum. But for the motor to work, you need a repetitive cycle, right? So here you can illustrate that. Say my system cycles between different chemical states. So this say there are two chemical states. Each chemical state for the rotor stator have this interaction. So for a given chemical state, because the system is symmetric, right? You have this periodic potentials. And another thing you realize, in order for you need the coupling between chemical reaction and this mechanical motion. So you prefer, or you require this chemical reaction should be has some dependence on your mechanical degree of freedom. Let's say they're only localized region, you can have the jump. Like in the motor, you have this ion channel. You need to have a rotate a certain angle, then the ion can jump on or off. So then you see, okay, if you have one state, there are thermal fluctuation, then it jumps, then you relax, jump to another potential, relax, then another chemical happens, go to there. So repeat the process. So you change from state one to two, then back to state one. But because mechanical coupling, mechanical coupling, then you do have right. You do not go to back to your system. First of all, you consume some free energy, right? This is out of equilibrium. That's you, and also there's a mechanical motion. Okay, so that's what happens. So you see a protein motor, you have this. You need to have multiple chemical states. It can be this ion hopping off, or there's a chemical reaction, ATP hydrolysis. Then you need to repeat the cycles, and it's dominated by thermal fluctuations. So this is important unique for this nano scale machine, and that's a mechanical degree freedom coupled to chemical reactions. Okay, so we also see this is not so different from a microscopic machine, right? Because microscopic machine here I showed Rango engine, and similarly also have multiple chemical states because this fuel, right, got burned. You need to repeat the chemical cycles, have mechanical degrees, freedom coupled to chemical reactions. Well, see, right? It's only the fuel got reaction at certain angle of this Ranko engine. The main difference here is, in macrocell machine, we thermal fluctuations is not a really issue. So we see similarity and difference. Then let's look at this Flagellar special. Yeah, we just use this very generic ingredient. Okay, we have chemical reactions that two ion need to hop on and off. So that will lead to my stator to have two different conformations. And that's well due to rotor stator interaction drive some mechanical motion. And then we have the elastic coupling, that's the hook, and they have the load, right? They're nothing special. we can definitely specify what's relative state interactions, but I just argued really matters, you require, satisfy the two time scale separation. Well, yeah, here I showed you have this ingredient. So let's just use the ingredients, well known, well documented in the literature by the experimental studies. Let's see if we can really indeed can recapitulate the model, the observation. And now you just formulate some mathematical equation. You can really, this is a low Reynolds number, right? You can write down a torque balance. And so write a Langevin equation. You can also change it to this Fock-Planck equation I wrote here. So right, they have diffusion, convection, the convection, and also chemical reaction, right? All this very standard. You can specify all those parameters, then do some analysis. Okay, so this is well, there's some technical things try to solve this equation efficiently because now you have to explore parameter. Then that time I have to really work out some algorithm. So I do need to develop some tools, but this because I need them. Then you see, indeed, you can recapitulate all the experimental observations. So this is really exciting because at that time, it's really, after more than a decade study, finally, we can use a model to explain what's going on with the data. So Howard got very excited. He took this work really seriously. I once visited him, and so he really asked me several times about all my details, the predictions. Even once in a conference at the Corsica Island, there's summer school at Corsica Island. I gave a post there. One day I saw him, just sit on a chair, stare at my poster for hours. So he thought about this. Then later he recruited a postdoc, Dr. Jianhua Yuan from Caltech, to test the predictions. So let's see. Oh yeah, I forgot one thing, right? Before this, let's see. I haven't explained, the what have we learned the maximum. The maximum. One thing I said that the plateau I mentioned is due to time scale separation, allow this thermodynamic controlled region. So mainly here, the two time scales I mentioned is 1 over the internal dynamics. Well, if you consider this mechanical degree, this really tell, you see, in order to get this region, you need the rotor, the system need to rotate to this region, transition region, then make transition. So it's effectively given by this quantity. And then this is the beat, right thing. So then you see, okay, if that's a time scale separation, it's the region you got this torque moment given by the thermodynamics, right, the driving force. But when you have this separation becomes not satisfied, you start to lose this efficiency. And also, but the question is why the sharp? That's a really a major puzzle. Well, turns out this can be understood from the two time scales. Well, as mentioned, because of the mechanical-chemical coupling, you see you have this relation, right? You need depends on your distribution on this potential curve. So let's think about, when you have high load, when you have a large load, the load is suddenly tilted potential, right? Because you have the effective potential like this. Now you see single system, you have multiple states. Remember, you have multiple states working together. And also they are because they are coupled. So they essentially move together relative to the rotor. So think about, okay, you have one stator move to this region, because this is have enough time come here, make a jump, then other stators around the middle time, well, then we move, jump to another curve, then start to move down to its own, minimum again. So that's fine. Everyone has enough time to make the transition. But thing is, when there's less load, so the tilting is less. Then you see the distribution got shifted. So in this case, there's higher chance for this stator before it's moved, enough time to move, try make the transition, or they push away by others to out of this transition region. Okay, so then your system stuck. When you're stuck there, you got enough time, more time for the spring to relax. So when you have more time to relax, you have less tilting, right? So that's this cancer. There's a kind of a positive feedback between the mechanical degree of freedom and the chemical degree of freedom. So this positive feedback lead to this sharp transition. Okay, so this is a clear explanation. So now let's see how the predictions. That's what Howard cared. Howard want to really try to test because in the past, every time you have a model proposed, and Howard will do some experiment, shut that down. So I kind of on the side I'm kind of little anxious, although I'm kind of confident my model. I was also kind of anxious to wait his test. So we show this, in those um, more stators, right? When they at the thermodynamic region, the more power generating units will give you more motor torque. But when you have high speed, we predict actually they will kind of destruct interference. As I just mentioned it previously, then they can really lead to, they have less motor torque if you have more generating units. Okay, so this is what unique for this connected controlled region. Okay, um, I think this is very intuitive, right? Think multi-cylinder engine. So you see, you have tuned those cylinders very well, so they can synchronize their work. Otherwise, if out of phase, they will really fight with each other. So it's I think very very natural. So Howard's asked Jianhua to did experiment. And unfortunately, this is what they observed. They didn't see, they say more torque, you have less with a zero load speed, right? When you have they use a gold nanoparticle, so they can read very small. That's very low load. They monitor the speed. What they found is they have different standard, about the same. Okay, so this has become an issue. So then we look at what's going on. We realize one thing. There's one component. This is a stator anchored to the polypeptide glycan. So this is elastic. We know it. We knew it. But that time we treat it. So we thought, okay, this is fast moving. We can treat it as a quasi equilibrium approximation. The reason is if we treat it explicitly, we got many degree of freedom. That's computationally expensive. So that okay, it's good enough for me to do this quasi equilibrium. We thought it's a good approximation. But turns out this is essential. The reason is why we need to go beyond this mean field type of treatment is the fluctuation behind important, right? Because you see, think about the situation. You have some stat that got stuck there. Because elasticity, others they won't be also stuck, move, right? They can also stretch themselves, make transition. So that will help alleviate the problem. So this is turns out one example, one place where I thought we made some good approximation. Turned out we made something important. I'll have another example later. And also intuitively can understand what's going on. I use this three-leg race. You see, as I just mentioned, what happens, if you have the low speed, slow speed, then right those the partner can coordinate well. But when higher speed, start to lose their coordination can fall, right? But so look at these two boys. They're kind of easily win, right? Can easily win. But to see the kids really they're cheating, right? See these two girls, they're very honest. They tie them very tight, right? Even the toothless. But this one, have very loose one. So make this much easier. So this is essentially what happens for the flagellar motor. They use this elastic component on the anchor to help to alleviate this destructive interference. I think this is a really clever design. So we also have another prediction, this torque speed relation. We say, okay, because this is due to thermodynamic, right, time scale separation, so the thermodynamic origin, we expect if you pull the motor different direction, you still have time scale separation, should have this plateau. So this is one, actually is one figure in the supplemental. And then that figure also predict, this is the elastic component is very important. If you do not have this component, then this is what the torque speed curve you would expect to see. Okay, in this one, see this direction is counterclockwise, this is clockwise direction. So Howard, they also did experiment, test on that. Again, they used some mutants, they can only rotate in one direction. But in this case, what they found is this. See, this is CW. It's not what to predict, you have also have plateau, but rather very similar to what predict with the, without spring. Okay, for this is actually at that time I already left, right? So this is later Jianhua's lab. They measured the one piece experiment. They repeat the measurement of steel block on this flagellum motor, but look at the two different directions. They found out this flagellum, the hook, have higher, it's more rigid in the clockwise direction. Well, if what about this, not surprising, right? Because this is superhelical structure. So the asymmetry is not surprising. And then this is our new paper mainly by as a postdoc work with Hao Ge's lab at the Peking University. So he showed, indeed, if you think about this different elasticity, then you can easily reproduce the experimental observation. But what it is more than that, right? He showed, okay, he can do this further analysis. Look here, he noticed in experimental, you notice this flagellum hook actually have two orientation. Remember, in the CW direction, it's more straight and also rigid. And on the CCW direction, it's softer and also a tilt angle. He did carefully analyze the system because people notice there are two rotations. One, besides this precession, they're also spinning, just like Earth or the Sun, right? They're spinning and precession. So the torque actually can put in two components for the precession and for spinning. So we carefully analyzed the two components. What he found out is in this direction, all the torque essentially consumed by mainly done by spinning, right? There's much less torque go to the precession mode. The spinning, well, supervised, just the flagellum spin, right, does not push the liquid much. While the precession is where really push the liquid body to move, work as propeller. So this is what happened in CW. It's mainly spinning. Motor torque really consumed internally, mostly. So it's like a car when you have detached, right? You have a clutch, you detach clutch, then you just consume the torque internally. While for this CW direction, where the CCW when the cell runs, then this orientation, the property of this hook allow that most of the torque will be output for precession. This is a very beautiful analysis. And that's why you can understand, how it happened. You see, when it's a tumbling mode, you see flagellum just straight, they just, rotates due to spinning. So that's a scatter around, right? That's what he observed. But for the running mode, those flagellum really, they have large precession, then they bundle together as a propeller. So this is what one thing. Let me see how much time. Oh gosh, I had a long time. So let me quickly mention another thing. So this is when the motor, they also can switch, right? So Howard Berg and a colleague, they found out this the switching is also a function of the speed, so non-monotonically. So this is again another puzzle. So I at that time I also look at this. I clearly remember this is one of the Gordon conference on statistical physics and biology. I was at the Breakfast table with Richard Berry. So I tried to use a napkin, writing a napkin to explain to him the problem. Then I suddenly got the idea. So what's going on? So let's think about what's going on. This is a motor. That's a rotor. There's a rotor unit. So the stator interact with rotor. You can the top view, and then this unit can switch to two conformations. Okay, this is what happens. So you can build a Ising type model. So the Ising model is, so you think about, you have two conformation, one CWD, CCW, and those you can bind KYP. The KYP, you have binding, unbinding state. You have four states you can switch. And that's this Ising type model by Dennis Bray. They assume, okay, the rotor unit, they also have lateral interactions, right? See this spin model. So then, if you keep the count, you can see there are some cooperativity that give this coherent two states. So then you can think of what happened. If you think about rotor state interaction, well, the motor not just torque, not just along the tangent direction, but also have components. Let's say compress the rotor. That way, say, let's assume that can also affect the switching rate. Let's assume here it is by the barrier. I should explain why I thought this way. Then you can see why you have this peak. The reason is okay. Remember the torque speed curve usually is a decreasing function as the rotation speed. So at low speed you have more torque, and the torque will help this transition individual unit you interact with. Okay, but in order for the whole thing so it's a slow speed, lower speed give you more help on the individual unit. But for the whole thing to rotate, you need to help more units. So fast speed, so at unit time, you can the one stator can really help more units. So that you see, there's a opposite effect. Then you lead this peak. So this is a very intuitive understanding, and this is exactly what I just immediately wrote to Fan to run the simulations. This is exactly what we observed to explain things. And also, I won't go through this one. So you can think about what's the possible reason, a function. Well, you can think about this can help detect the obstacle, right? We stuck there to help the bacteria to switch and explore other regions, other directions. And also you can think about can help the stator, the motors, different motors to coordinate, right? One change direction or push other to change. So this is actually this slide I made more than 10 years ago. Now recently I convinced a collaborator to work on it. But I want to point out one thing. This is what I missed. What I say is in that paper more than 10 years ago, we assume this only affect the barrier. The reason I did this, right, in principle can affect both the weight and the barrier. The reason we assume this, if you think there's some free energy will change the relative weight, relative height. Well, you have to explain where the free energy comes. Well, of course, come from the ion motive force. You need to explain why, how this change, some will be used here, so how that affect the motor torque, many other things. So I thought, well, okay, they're too complicated to explain to the reviewers. So let's just use the simplest assumption to barrier. Then you don't worry about that. So you see, right? Only change the prefactor. That's good enough for me to explain this. But the interesting is recently, Henry Metley and Yu Hai Tu, they re-examine essentially the same model, but the larger parameter space. And they found, right, so they relaxed this constraint, and they found out if, you can change the relative weight by borrowing some free energy from the ion motive force, then they found out that can be utilized for the switching. Even they said you don't need this cooperativity between the motor, the lateral interactions. That'd be good enough. And they showed that will sharpen this dose response curve right? The chemotaxis. So this is a very interesting thing. I thought, see, this is I thought I made a reasonable judgment, but turns out I missed something important. If we explore this in larger space, we'll see this. So let's go back to my old question. I want to ask is, I want to utilize the old experience to get questions. My idea is actually in this old study, I really, inspired by all this advice from advisors and previous old generation researchers, Hamlet. I think my argument is in new time, in big data time, we still need them. Actually, this big data, all this AI will facilitate us. Now we can, because we need to collect the information, then our brain process it, got all the intuition process that thing. Now it's much easier to collect the information. But so in this time, I think this physical intuition, this physical thinking is more important. And this is the question is how our community should kind of communicate, advocate to large community and show the community that we have unique strengths. So this is something I really want to raise for discussion in the field. Okay, I'll stop here.